Hey everyone, continuing into inverse functions, we'll now explore the relationship between function and the inverse. Alright, so we start off with a very simple idea is that we know that if we have y equals to fx, the x is basically the input and the y is the output. Right? So we basically have the domain of f as the input and the range of f as the output. But in an inverse function, what happens is that after replacing y with x, we get y equals to f inverse x. When we input the x, right, because we must note that, well, this basically came from x equals to f inverse y. When we put in x, right, we're basically putting in y, which is the output. Therefore, we have the output, right, which is basically the range of f. Then y is the input, which is the domain of f. But because we have graphed the inverse function in terms of x and y, where x is the input, we can then conclude that the domain of f inverse is equals to the range of f, and the range of f inverse is the domain of f. So these are two relationships you need to know between our function and its inverse. Another relationship is actually through the graph, right? So let's say we have the xy axis, and let's say we have the graph of y equals to fx. Let's say something like this, all right? Y equals to fx. Now, the f inverse graph is actually a reflection of the fx graph about the line y equals to x, all right? So we'll get something like this. Okay? Now, so this is the inverse graph. So why does this occur, right? Because if we were to reflect, because I understand that the input of x, the input of f, right, which is x, was the domain, is now the range for f inverse. So the idea is that if you had the point AB, where we had in the original graph, right, we had AB, where A is the input, B is the output. In the f inverse graph, it'll be the opposite, right? Because your input becomes the output, your output becomes the input, right? Therefore, BA. And we achieve that by reflecting the graph about the y equals to x. Now, the idea is that for any graph, right, let's draw another axis. If we have the general point AB, then from the laws of reflection, we know that the shortest distance would simply be this, right? From the point to the line. This distance is then replicated on the other side, keeping a straight line, right? And then you get the reflected point. Let's say we have the green point being the reflected point. So the idea is that now, if you compare the points, right, let's label the green point as B, the reflected point, and the red point as B as well. Okay, maybe the reflected point is B prime, right, to make it more mathematical. So from here, right, you notice that the line B prime has a perpendicular bisector of y equals to x. And what does it? And if you notice, right, any point on the line y equals to x, let's say we have this point right here, this distance to B would also be the same distance from that point to B prime. And because of that, if we were to have a point on the line such that it is now we make a right angle triangle, right? So let's say we have the point here, we draw a line across, and this is a perfectly horizontal line, and then this line downwards is a perfectly vertical line such that it makes a right angle. Because this original point B was AB, which means horizontally, this is basically a y equals to B line. Therefore, from here, it's B comma B, because it's on the y equals to x line. The distance here, right, is B minus A. All right, and because the idea that any point on this y equals to x line is of the same distance between B to that particular point and that particular point to B prime, this distance here would also be B minus A. Therefore, since this is a perfectly vertical line, the x coordinates remains the same, but the y coordinates will now be B minus A. So B minus B plus A to give us B comma A, which is therefore our inverse graph. All right, so this is the reason why f inverse x is basically a reflection of the fx graph about the y equals to x line. All right. Now, the last relationship you need to understand is the idea that f inverse fx, so, well, f inverse, then putting f, substituting every x with fx, equals to f inverse x equals to x. All right. Now, why is this so? Let's take a look at the first case. All right. So we have f inverse fx, right? Now, we know that fx, right, the x you input is the x you put inside is the input, right? Then fx will then give you the output, right? So let me just put it easily. So, okay, let me just rewrite this. So the x you have at first is the input. So you put fx, this is the input. Fx results in the output, right? Now you then apply f inverse. F inverse on the output, you'll get back the input, which is basically x, right? If you notice, it's right here. Now we look at the other case. We have x. Now we put f inverse x, right? F inverse x, right? When you put x inside f inverse, you're basically putting the output of with respect to fx. When you put f inverse x, this gives you the input. Now you put f outside, you then have f bracket of input. F input will basically means giving you the output. And because in f inverse x, the x you put inside is the output, this then gives you back x as well. Alright, now this is actually useful because in some questions they'll ask you to solve, for example, f inverse x equals to fx, or f inverse fx equals to fx, which means basically asking you to solve x equals to fx. Alright, so this is another relationship you need to know about our f inverse and fx. Alright, so there we have it, the relationship between fx and f inverse x.